Hi, everyone. I'm Viktor Sesson. I coach product and tech companies. And my clients typically approach me like they've either tried the radical autonomy empowered team and they got everything wrong, the anti-patterns from yesterday, or they tried the scaled frameworks and they got big, slow, and expensive. And I help with org design, product strategy, and I work a lot with team dependencies. Before I get started, I'd just like to ask, what's the fastest way to make all of your team or all of your meetings end on time? You might think that it's adding an agenda. You might think that it's actually like having a facilitator or doing speedy meetings, but it's the opposite. It's actually making them longer. And if that surprises you, welcome to stochastic noise. And that's what I'm going to talk about today, stochastics and probability distributions. So stochastics essentially is the inherent randomness that exists in a system. It's irreducible, so you can't get rid of it. We try to plan, we do big room planning and stuff like that, because we think that if we get rid of this, all the uncertainty we have, things are going to happen the way we want to. But it's actually the opposite. The more we overplan, the more we do, the greater our stochastic surface area is, the more randomness we get, and the less we actually get the things we're hoping for. In mathematics, it's explained through this equation. It's a non-linear stochastic difference equation. Looks fancy-pantsy, sounds fancy-pantsy, but it really means your outcomes is a function of three things: your current state, the actions you take, and random noise. And we kind of always forget the random noise. So that's what happens in the meetings, right? I mean, first of all, nobody likes to interrupt Lars, so that's why they run over. But also, there's always someone late. There's always an incident. HR and security, they kind of like, oh, we want all the teams to talk about this thing. Someone missed a meeting, and they have to get caught up to speed. And all of these things are the stochastic noise that's playing out. So I just want to show you a little bit. So in terms of meetings follow a right-skewed probability distribution, which means that there are a few events or a few things that are going to kind of drag up the mean significantly. This is also true for backlogs and on-time deliveries, which is also why reducing backlogs is a good thing, because the smaller your backlog is, the lower the mean is, if you want to think about it from a math point of view. But the distribution I really want to talk about most today is S-curves. S-curves are distributions that show you where there are thresholds and tipping points, and team dependencies follow S-curves. Now, S-curves can look a little bit different. You can have an early threshold point, or you can have a late one. When you're in the threshold point, nothing really, before you cross over a threshold point, nothing really happens to the system. You don't trigger the system to behave in a new way. But once you get to the threshold, you tip the system. So you have one area which is exponential, and then you get to a plateau. Once you're at the plateau, again, things don't really get that much worse. If you're thinking about this from the point of view of team dependencies, if you're down here with dependencies and you add one dependency, it doesn't really matter that much. But if you, as soon as you get to the exponential zone, the more dependencies you add, you get into a catastrophic situation. Now, fun fact, love follows an S-curve. So, some people, they get to a threshold or the exponential zone very fast, and some people take a long time. So this would be my wife with me. This would be me with my wife. However, this was my wife with me, and this was me with my wife. So I got interested faster. She fell in deep love faster. And yes, we did talk about this. Now, so really what I'm talking about here is that data is great. Yes, yay, data. But if we don't understand the model behind the data, the model that's driving the data, we don't really understand what the data is telling us. Probability distributions, they don't help us predict the future, but they help us understand the general tendencies of the problems we're seeing. So they can explain, these are the probable things that are going to happen, but they can't say this is the exact thing that's going to happen. Now, if we have the data and we have the model, we can start to do some fun simulations. So here is a general model I built. And if we look at let's just make this a little bit smaller here. So, okay. Let's say we have an organization with 8 teams. Fairly standard. You have 8 developers per team, and you have an average hourly cost of $70, and you have 1.5 in dependency saturation. You can see that the meeting costs are $28,000. The communication per team is going to be 12 hours. That follows a right skew, so this is actually a combination. And then you have on-timeliness of 90%. Now, if you in this situation want to increase your throughput, you might ask yourself, are we going to add more people? Are we going to split the teams because they're big? Or are we going to reduce the dependencies? Well, since if we reduce the dependencies, we don't really get that big of a difference. We get a small difference. We cut the cost a little bit. We increased on-timeliness a little bit. If we add 20% more people, we reduce the on-timeliness, but we're actually increasing the throughput. So that might be a fair trade-off because we're at the bottom. We haven't even gotten to the exponential zone yet. However, let's see what happens when we play with the dependencies. So if we go up to the half, you can see that the on-timeliness suddenly very quickly drops because we're now in the exponential zone. And if we go up a little bit more, it continues to decrease, and then we get here. And from here on, it doesn't really get worse. You're in hell. Okay, it's 1 degree hotter, but you're still in hell. Now, what usually happens is when you're about here, this is when people start complaining to engineering managers in meetings, or to product owners, or product owners complain to their managers. And they're like, okay, you know what? We need more people. Things are taking more time. But what actually happens is that you make things worse. And that's because of the stochastics. First of all, you're tipping the system to the plateau. And when you're doing that, you're adding stochastic noise. Now, in this case, we can start to explore what would be better. Would it be to add more people, split into more teams, or reduce dependencies? And obviously, it's to reduce dependencies because you're moving the system back below the exponential zone and you're reducing the stochastic noise. So these are just some of the things that we get and we can simulate and model when we have probability distributions and data. The last one I want to talk about is the power law. And the power law is pretty interesting because it talks about how really you should pay attention to the tail events. The tail events carry disproportionate impacts. If you're thinking about this from the point of view of total cost of ownership for software, it says that a very, very few or limited amount of decisions are going to carry more or less the majority of all the cost. Now, if you're a CTO, this really matters. If you're a PM, this also matters because, as you all know, a few features will essentially carry the entire revenue, or a few customers will carry the entire revenue. So if you can model this, you can start to predict which decisions are more important than others. For for total cost of ownership in software, the most expensive decision, just as an example, would be should we even use software? Not build versus buy, which I've written here, but like should we even use software? Like that's the most expensive decision you're going to make. Period. Then the next one is like, okay, do we do build versus buy? Now sometimes you do build, and then 4 or 5 years later you make the same decision, the build versus buy decision. So these decisions, they're not always linear and come in like a very, very ordered sequence. They can happen anytime during the entire life cycle. But we can see that a few key decisions are the ones that matter a lot. And if you know this, then you can look at what is the tail effect of this decision and spend your time there instead of talking about things like should we move this button from here to here? Do we split this function out into this place? These are insignificant. You shouldn't spend too much time on them. So that's what power law tells us. Now, when we're working with organizations, it's combinatorial. So like all of these probability distributions come together. And so it's really good to be aware of the ones that exist. Now, I could speak days about this, but I'm just going to start wrapping up. There are kind of like just arguments in relationships also follows a fat tail or a power law. So a very few limited amount of arguments are going to determine or dictate the entire relationship or the dynamics. So that's also like, this isn't just for math and organizations. This is for a lot of things. Also why, for example, Yassal, who's sitting here with fix it now or delete it, that whole thing, like delete your backlog, you remove the tail events by removing the size of your backlog or by removing the amount of defects you have. So these are some great decisions you can start to make once you understand probabilities better. My name is Victor. Thank you so much for listening.